Welcome to Cryptography and Hardware, the last session. Yeah, you already learned a lot about how to implement different security and cryptographic primitives in hardware, VHDL, FPGAs, and so on. And today we review some basics about some other topic, which is called physical attacks, which is the main topic of another lecture of mine. And if this is interesting to you and then you found it interesting, of course, you are welcome to join the lecture in the next coming semester. First of all, before explaining you what are physical attacks, we have some definitions that you heard for sure. I mean, like Kirchhoff's principle that a crypto system must not be required to be secret, and it must be able to fall into the hands of the enemy without inconvenience. No? For example, we have the AES or some other secure algorithms. When the algorithms are actually secure, but the security relies only on the secrecy of the key. But here, what is important is that you have implemented a device and you have already implemented AES in many different forms that you have learned. Now you give this implementation to the adversary. How you give it? I mean, of course, you don't do it intentionally, but you implement it in some application, and the application is used by the adversary. For example, in the ETC card, in some key fob of the cars, in your mobile phone. I mean, everywhere that you implemented the cryptographic primitive in hardware, usually, or microcontrollers, they are used by the users, and the users can play the role of the adversary. And the idea is that in physical attacks that they will review, is that, of course, everything is fine, the implementation is very well. For example, the AES is super fast or super small, depending on the requirements of the application. But one problem will be that the implementation is not secure. What does it mean? It means that the adversary has some opportunities to reveal or recover the key of the AES that you have inside the implementation, and then clone your system completely. It means although the AES is fully secure, but it's possible to recover the key of the AES that you have implemented. And then one important thing is that we define a cryptographic scheme for a given task, and if we say this is secure, if no adversary of a specific power can achieve a specific break. For example, you say the AES is secure because under which adversary model? If you say the adversary is able to do the exhaustive search, then it's not secure. But the adversary model that you define, okay, the exhaustive search is not possible because it takes very long. Then you consider it as a secure. And then you have to always define an adversary model, and under that adversary model, then prove the security and say or claim that the implementation or your scheme is secure or not. Then the definition of cryptographic devices, this is what you already learned in this lecture. Means that, for example, the implementation that you have of AES or any other thing, which actually performs a cryptographic operation. And one thing that we have, what is super important, not only in the implementation, for example, you say the security of this implementation should not rely on the secrecy of the implementation. It means that you should not build something and say, okay, I don't give this information to anyone, but it's secure. I claim it, and then I keep the implementation completely secret, and nobody has information about how I made my AES. And then I claim also security because somebody has to reverse engineer first my implementation and then find out how I implemented the AES. And then breaking a cryptographic device that we will see today means extracting the key of the device, not breaking the underlying algorithm. If you make the AES on one FPGA and then I break your implementation and I find the key that is employed or deployed, and then it doesn't mean that I broke the AES. I broke just your implementation of the AES. One thing which is already outdated, but the topic is interesting to say, these physical attacks actually came to the market first by one application called Pay TV system. Yeah, at the moment, you don't have this application anymore. I mean, everything is over satellite, and then of course the receivers are also connected to internet at the same time, and then you have a subscription, and then you can watch scrambled channels, yeah, easily, without doing anything. But many years ago, it was not like this. Yeah, when the receivers were not connected to internet, and then you had to buy a card, a smart card, like the EC-Karte. Did you see there is a small chip on it? And then put the card inside the receiver to be able to see the scrambled channels. And then you had to pay for the card. And then, of course, there were a lot of activities of cloning these cards, no? And then sell them in the black market, for example. And then if this is, of course, a good ones, good broadcasters had very good cryptographic primitives there. And then if you break the implementation, break the cryptographic implementation, which is there, and find the key, then you also can clone it. And then afterwards, after these attacks came out, then the broadcasters try to actually change the key very rapidly. It means that every day or every hour is the key is changed, and then the receiver had to be connected to internet to be able to get the set of the keys and so on. But now the business model is different, and these keys, these smart cards are not mainly used anymore. Some examples of cryptographic devices you already know: electronic money, for example, ID cards, passports, remote controls of the car or garage door openers, or USB tokens and some RFID tags, the transponders you have for opening and closing the doors, and many other things. And then, of course, there's always fun and huge interest to break these implementations, either for financial gains, for fun, for illegal copying, and so on. The physical attacks, actually, as I explained, they try to find out what is the secret which is inside the implementation. And the attack scenario is like this: the attacker has a legitimate or is a legitimate owner of the device, and can also use the device showing that she is an honest owner, because it's a user. For example, you have an EC-Karte from your bank, and then you are the user, you can play the role of the adversary. And then you can also manipulate, disturb, and also observe the behavior of the device. Means that if you have a terminal of your EC-Karte, and then EC-Karte, you put it there in your lab or in home or your office, then you can do whatever you want with the terminal. It may happen that it doesn't work. You cannot communicate directly with the bank, but you can do whatever you want. And then the goal of the attack is to find the key which is inside. And sometimes the key is a session key, means that every time that it communicates, or every couple of hours or minutes, the key is changed. The idea is to just find the key. Of course, the easiest is to find the key which is permanent there inside the card or inside the device. And once the secret is revealed, then the security is gone, because the security entirely depends on the secrecy of the key. Good. Physical attacks, examples of the attacks on cryptographic devices. Physical attacks or one physical attack means to use the physical properties of the cryptographic device to break it. For that reason, you need to have physical access. And then I will explain you a very, very simple example, which actually doesn't deal with the cryptographic devices. It's just a device, and then you have probably a better understanding of what I mean. Suppose that Eve finds a USB stick with a secret data on it. And then to access this data, you need to enter an 8-digit PIN. And then the device has a delayed response, means that every time that you enter the new PIN, then it takes 1 second to say it's correct or not. And if you want to do a brute force, then you have 10 to the 8 possible pins, and then it takes roughly 3 years. And the idea or the question is whether the attacker has a better option. Then suppose that the attacker, or she or Eve, knows the implementation platform. For example, it's a microprocessor, and a part of the software is responsible for pin checking. Somewhere anyway in the microprocessor, you check whether the given pin is the same as the one which is stored inside. And usually it's something like the STR comp, yeah, or memory comp or something similar to this. Yeah? And then, if the first digit or first digit of the pin is wrong, then it terminates and says, okay, this is wrong. But if the first two ones are correct, the third one is wrong, it takes a bit longer to answer you and say, hey, this is wrong. Yeah? Then the execution time of this process is data dependent. Yeah? It depends on the number of clock cycle or time. And then if the pin is correct, it takes much longer. If the first digit is wrong, it takes very short. And then how to attack this? The attack is easy to by measuring the time. Means that the attacker needs a device to measure either the time based on, for example, nanosecond, picosecond, microsecond, depending on the device and technology. Sometimes measuring or counting exactly the clock cycles, but sometimes the clock cycle is not known, then you need to exactly measure the time. Yeah? But then the time from pressing the enter of sending the pin and getting the response. I mean, this time you can measure. And then the attacker selects just the pin and change only the first digit while measuring the time. Then you have a set of, let's say, set of 10 running times, and then the one which is shorter than the others, the one which is longer than the others will identify, okay, for which one the first digit is correct. Of course, this is imaginary, but then means that the attack doesn't actually work like this. Then you need to measure many more times because sometimes you have noise, sometimes there are something else in the microprocessor, sometimes you have a very big offset with respect to pressing the enter and then getting the response back. And then for that reason, you may measure this many more times and get average. Yeah? But in average, just one of them is longer than the others, means that the first digit is correct for that one, and then it checks the second digit. And then you do the process 8 times, means that the first pin you find, and then fix the first pin, and then change the second pin, second digit of the pin, and you continue like this. And then in theory, 80 timing measurements are enough if you don't have any noise at all. But if you have noise, then you have to multiply this by a factor depending on the noise. Yeah. Then you need to fix this. Means that you make the steer completely fixed and independent of the given pin. And then, of course, if you guarantee that it then completely the running time is independent of the given pin, then you have protection against this attack. Yeah? But the question is whether the attacker has any other chance. Yeah? The chance is, for example, measuring the power consumption. Yeah? Most of the digital circuits are implemented by CMOS technology. I mean, we talked about this, and I mean, most of the mobile phones, the processors that you have, almost processor in PCs, in mobile phones, in key remotes, microprocessor, everything is made by the CMOS technology. And then the power consumption of this processor depends on the execution of the executed instruction, also process data. For example, if you have a microprocessor, and then it has instructions like the AND operation and also ADD operation. Yeah? And then the power consumption of AND is different to the power consumption of the ADD. Yeah? It's one thing, I mean, there is a dependency between the power consumption of a device and the executed operation. At the same time, if the operations are the same, for example, you have 2 AND instructions, yeah? But the operands are different. Again, the power consumption depends also on the operand. And this information you can use to understand what is going on. Means that the attacker should be able to measure the power consumption during the pin checking process, instead of measuring the time. Then we will see one slide about this, that you measure the power consumption over the time. Over the time you measure the power consumption, then you see exactly at every, for example, nanosecond or picosecond, what happens inside the device. How much power is taken from the VDD pad. And then again, the same process means that the first pin is different, the first digit of the pin is different, and you measure 10 power traces. Or again, if it's noisy, you measure more and then get an average. And then one of these power consumption traces should be different to the other ones. Now, to the other ones, and then you then identify which digit is correct for the first pin, and then you continue again this process. Of course, this is complex. It's not as easy as measuring the time. But the complexity and the noise problem is the same as the timing attacks, or the attack that I have explained based on the timing. Then overcoming this problem is not as easy as you think. I mean, it's not as easy as timing attacks or timing dependency, because in timing you should just make sure that it's constant timing. But it's absolutely impossible to say that I want to build something which has a constant power consumption. And this is absolutely not possible. Now, many people tried it, even in the transistor level. But still there is a dependency that you can recover, and you can identify this dependency and make use of it to perform an attack. And then there are many other scenarios, and this is actually one of the research topics, how to overcome this dependency of the power consumption to the data which is processed, or the operation which is performed by the processors. Then even if you do it, you are able to, for example, make this possible, that the power consumption is independent or is constant. If we imagine this, then the question is whether there is no physical attack possible. Again, it depends on the adversary model. Then you change the adversary model and say, the adversary is able to make some problems and disturb the device. Means that inject some malicious faults into the system. For example, by something which is called clock glitch or power glitch. What are they? The clock, this is what you have learned. It's something like this. And critical path delay. You learned this, that this is, for example, T, and the T should be larger than critical path delay of the circuit. Now imagine that I actually keep the clock, but for one of the clock cycles, actually I change it like this. This is T, but this is a small t. And the small t is smaller than critical path delay. But then it means that there is no guarantee that in this cycle the circuit works correctly, because critical path delay means that the longest path into the implementation means that it's not always the longest path is active for every input. For some inputs, the input has to pass through this critical path. For some other inputs, no, the output of the combinational circuit is already ready and can be stored in the register. You already learned milli and more machines. This is the milli machine or more machine, it doesn't matter. You have here the combinational circuit, and you have some registers. And what does it mean? The critical path delay, for example, the path from here to here again. And then if for some inputs, some state of the circuit, the output of this combinational circuit is already ready to be stored in the register. But some of them need longer time. For that reason, this T, when you decrease the clock cycle for one particular cycle to, for example, T, then for some inputs, still the circuit works correctly. For some other inputs, it doesn't work correctly. And then if you distinguish these two cases, for which input it works correctly, for which input it didn't work correctly, you learn already something about the key. In this dependency, you can exploit. This was, for example, the clock glitch. Another one is also very well known as the power glitch. For example, you have your chip, and this is the VDD of the chip, ground. And then what I have VDD here over time. And for example, the VDD should be 1.2 volt, should be something like this over the time. But then in one point in time, I make it lower. Yeah? This is a glitch of the glitch over the power, but of course it doesn't look like this. I mean, it will be something like this. I mean, if you bring it down and then close it up, it will be something like this. And then the question is up to which point you should decrease it and what should be the duration of this glitch, of power glitch. This has different effects. Yeah? Again, some values which are inside the circuit will not work correctly because when you decrease the VDD, the gates which are in the combinational circuit, they become slower. Because their speed depends on the VDD. If you decrease the VDD, they become slower. Of course, from one point, you cannot increase it, because if you increase it, for example, from the nominal voltage, there is no guarantee that the circuit stays live. It will completely burn. But if you decrease it, again, there is a limit. If it's below, for example, 0.7, then no guarantee that it works. But 0.7 is still it works. But 0.7, you bring it down to 0.7, for example, the gates become slow, then you don't need to change the clock, or for example, you don't have access to the clock stays valid as it is. But in one particular cycle, you make the combinational circuit slow in a way that, again, the output is not ready to be saved in the register. One common fault attack which is performed on microprocessors is to do the clock glitch, and then some instructions will be skipped. This is a very common effect in microprocessors. For example, you have a microprocessor and then from instructions, you do a clock glitch in particular cycle, and then the instruction is not executed. The PC program counter of the microcontroller is increased. It goes to the next one, but the output of the combinational circuit of the ALU is not stored into the registers. This is a very common one. There are many more types of these attacks, like laser beams and electromagnetic effects. You have many options to disturb the operation of the circuit. And I have to say that performing attacks, these are called fault attacks. It's relatively easy to perform fault attacks on implementation of the cryptographic schemes if there is no protection. Because against fault attacks, you need to, again, have some redundancy in the implementation to check the correctness of the output. For example, simply you run the AES 2 times, and if both of them produce the same result, then you say, hey, this is the ciphertext if you have the encryption. Of course, then the running time is doubled. But or you have 2 instances of the AES, and then you do it at the same time, and then the area is doubled. There are many other schemes. I mean, there are simple scenarios, but there are many other schemes to provide security against fault and security against fault attacks. But again, these fault attacks also, the security against them depends on the adversary model. For example, even if you have 2 instances of the AES close to each other, you can imagine that one attacker injects 2 laser faults into exact the same gates, and then they produce the same output, and then the output is also not true. But it's the same in both cases, but the fault passes through the check. But again, it depends on the adversary model. If you assume that this adversary model is not a valid one, then your implementation might be considered secure. The same can be done in this USB stick, what we discussed in our example, and then during the pin checking, we can actually skip over this instruction, and then pass this. If we find out exactly at which clock cycle we have to do the clock glitch or the power glitch, and then this check is passed, and then you can access, you can have access to the data which is in the USB stick. But by this attack, in this particular case of the attack, you do not find the key, you do not find the pin, you actually pass this check, and then if you want to access again the same data, you have to repeat the attack, which is not the case in the timing attacks or power attacks. Then there are many different kind of attacks, physical attacks. There are different categories. They are classified from the attacker's behavior point of view to passive attacks and active attacks. Now, passive ones, where we measure the timing, when we measure the power consumption. There is also a way to measure the electromagnetic radiation. And active attacks are those that we, for example, inject fault. You know, we make some disturbance and problem for the device. And from another point of view, we have invasive, semi-invasive, and non-invasive attacks. Non-invasive attacks means that the device is as it is. We don't make any modification on the device or its package. In a semi-invasive device, you can depack the device, because there is a device has a package, plastic package or ceramic package or some form of metal package or cover. Then you depack it. You can have reach, for example, the silicon of the device, exactly the gates and the transistors, but you do not make any electrical contact. Now, for example, by some laser beams, you can see, watch, or you can observe, or you can change it by laser beams. And invasive attacks means that you don't have any limit. Just open it as you want, change anything that you want, place the probe, have some electrical contact with the device without any limit. No? The danger is actually, most danger is with the passive and non-invasive attacks. Means that physically you do not make any modification of the device. Then if there are some facilities inside the chip to detect tampering, then you do not make any changes and the tampering will not be detected. At the same time, it's passive, means that you, for example, you just listen to the device, listen to its power consumption, listen to its timing which is required to perform, for example, the AES encryption. Then the device doesn't have any facility to understand that somebody is listening to its number of clock cycles or counting its number of clock cycles. Then protection against these attacks is the most dangerous or most difficult ones. And based on this categories, we have 6 different attacks, 6 different class of attacks, and passive and active and invasive and semi-invasive. And one category is called site and analysis attacks, as is exactly what I have explained. They are non-invasive and they are passive. And for example, the power analysis attacks fits to this, means that we measure the power consumption. Timing attacks fits to here, then we measure the timing. Electromagnetic analysis attacks also fits to here. Electromagnetic analysis attacks is similar to power, but instead of measuring the power consumption, we measure the electromagnetic radiation of the chip. You may ask how? This is, for example, the chip. We have a cryptographic core, cryptographic device. We put a resistor here, resistor into the VDD pad or in the ground pad. Then when the VDD is fixed, for example, 1.2 volt, then the current which is passing through the cryptographic device depends on this operation. And then you want to turn this to voltage and then measure it by some oscilloscope. How do you do it? You put a small resistor here. Can be 1 ohm. For newer technology, it should be actually smaller than 1 ohm. 0.1, 0.2 ohms. And then measure the voltage drop over the resistor, because none of the pins of this resistor is connected to the ground, and the ground of the core is usually connected to the ground of the oscilloscope. Then you should use a differential probe. Means that it measures the differential voltage over the resistor completely independent of the ground, and then you can give it directly to the oscilloscope and measure. Or what you can do, you can have here the voltage over the cryptographic core, not here, but then one side is the ground, you can connect it here. But something, I don't know, probably you have, if you have studied only computer science, you may not have seen oscilloscope in your life, I don't know. But if you have seen, there are different modes of the coupling. It's AC mode. AC mode means that this is your signal, this is time. And this is, for example, volt. One signal, which is, for example, 1.2 volt, and it's changing like this. This is measuring in DC. Means that you exactly see is 1.2 and it fluctuates a bit at the top. AC coupling, when you want to do a measurement in AC, that means that you completely remove this DC shift. It comes down. Then it will be around 0. These fluctuations means that then you can increase the sensitivity and, let's say, zoom in. Of course, it's the electrical and analog domain. Then you make it larger and increase the sensitivity of the oscilloscope, then you can see the voltage peak to peak in a much better accuracy. Because these oscilloscopes actually are digital oscilloscopes. They convert analog to digital, and then this conversion is also not ideal. For example, they have 8-bit or 12-bit A to D. A to D is analog to digital converter. You have a voltage 1.2, but you want to convert it to digital to have some value 1.2 and then 0, 0, 0, 1, 2, 3, and so on. I mean, this with some accuracy you want to measure it. And if you have here both sides of the crypto core to the oscilloscope, then you have to measure it at the AC mode. Otherwise, everything is at 1.2, and then it's fluctuations that you want to see, you don't see. Then you have to bring it to the AC mode to be able to measure. Or you see a lot of noise, and then you amplify it and then filter it with some DC blocker, and DC blocker works actually similar to the measuring with the AC coupling. It's too much electronic at the moment, I know. Or you can have a current probe. You see the resistor is gone. There is no resistor, and the connection is actually dropped. There is no connection between them, but then it goes through the current probe and comes back here. And every current which is passing through here, of course, a dynamic current, is converted through a coil to voltage, and then you can easily measure it by one oscilloscope again. And then the current which is passing through here, the dynamic current consumption, is turned to voltage, and then you measure it by digital oscilloscope. Or, I mean, these are all ways. Or if you see I don't have any option to put this resistor on the board, I mean, it's too complicated, and the PCB is somehow and in different middle layers of the PCB, and then I cannot change it, then you can put an electromagnetic probe at the top of the chip and then measure the electromagnetic radiation, which has somehow a similar effect here. I don't know whether I have some figures and photos for that. Yeah. These are, for example, the FPGAs, some FPGAs that you have used. I mean, you use Arctic 7 in the entire lecture. Here you see Virtex 6. Zinc is one of the also here from 7 series, Spartan 6, and it's another FPGA that I don't remember. I mean, decapped. Here you see is decapped, and they are the bonding wires, means that the package is connected to the die. And here is the plastic package. Here is the flip chip. Flip chip means that the chip is there and it's just flipped over the package. But here is not flip chip. Here the silicon is there. You need to connect every pin of the package to every pin of the die. And here you see a metal cover over the chip. And if you want to measure the EM, electromagnetic radiation of the chip, you can put the probe on top of any of them, but not here. Here is the metal package, and you have to remove the metal package. And here are some large probes, and one of them is similar to the chip that you have. I mean, this is Basis 3, what you see here, which is from the same company, for example, Digilent. And then you have CMOS A7, which has the same FPGA with Arctic 7 FPGA, which is here. And then you can have, of course, a large EM probe, which gets a lot of EM radiations of the chip, but it's not localized in one particular point. It gives you a rough amount of power consumption of the device. Or you can have a super tiny localized EM probe at the top of the chip, and this chip is super tiny. I mean, this is roughly 3 millimeter by 3 millimeter, and the diameter of this probe is 150 micrometer. This is super small, super tiny. You cannot control it by hand. Definitely you need some devices to control this. And then, but this is localized. I mean, you can exactly get the EM radiation of one particular part of the chip. I can give you one example about this, how these attacks, I mean, not exactly how these attacks work, but one of the things that, I mean, I made myself busy with this roughly 15 years ago, and this was my first side channel attack on a real device. Here there is a transponder of the car, meaning you communicate with the car. And then there was a keylock algorithm inside. Yeah, this is a keylock. I mean, we did not talk about the keylock in the lecture. It's the algorithm of microchip company. And it's used for the key fobs. Means that you press the button and then a counter is increased and then the data is encrypted and then sent to the car or to the garage door opener, and then it decides whether, okay, I have to open or close the door. And here is one power consumption trace. I mean, I talked about the power consumption things, but I never showed you a power consumption trace. And here it is. I mean, here is super slow implementation. You see time is milliseconds. Yeah, means that is from 5 milliseconds to roughly 30 milliseconds. Yeah, from here it was waking up probably. Yeah, and then after some months we found out, okay, this time is writing into the EEPROM, because when you press the button, the counter inside the remote control should be increased. And then at this point, you see that, okay, this sends the data out, and then we understood that actually keylock is happening here. And then analysis were performed at this point in time. Of course, we first did the analysis here, and we didn't find anything. Yeah, and then we found out actually keylock is here. And then it was completely a black box scenario, means that you didn't have any information about about the implementation, how the keylock is really implemented into this. Either it's a microcontroller or it's an ASIC, no information. That was a single chip which performed this operation. And then by improving the attacks, finally 10 measurements were enough to clone the remote control. Means that you need to just have 10 of these power consumption traces and then recover the key and then clone the key fob. Yeah, this was one of the side channel attacks performed in the real world, and the devices that you can find in the market still. Yeah, I mean, if you go to garage door openers and the market, you can find still the devices which work with the microchip products. Yeah, for example, you see HCS. HCS is one of the or indicator for some of the chips which are from microchip, and they have also keylock inside. Okay, that was all. I hope you learned something in the lecture, which you may use for the future, either if you work as in a company as an engineer or as someone who is specialized in the IT security, and somebody comes to you and say, hey, can you implement AES? We want it very fast, and then you know what to do. Yeah, or post-quantum cryptographic algorithms that we didn't deal with in the lecture, but then it's roughly the same scenario, but you need to use a lot of other components like the RAM, yeah, because they are not as easy as AES to be implemented. You have seen that implementing, for example, RSA is not that easy. You need these multipliers, and then building the multiplier is not that easy in hardware. It takes either time or it needs a lot of area. And as I said, for post-quantum schemes, this is roughly the same. They're roughly the same. They need either very much area or they are super slow. Yeah, I mean, then it gives. I hope that it gives you some idea if you face such challenges in the future, either in your study or in your research or in your work future in the future. Then you know what to do for what you should search and find out the solutions.